Hello guys, in this video I am going to solve this question number 21 of chapter 8 from this book Engineering Circuit Analysis by Hayt, Kemmerly and Deriving. So the question is that for this particular circuit it is given that the switch in the circuit was closed for a very long time prior to be thrown open at t equals to 0. So before opening this switch, the circuit was in the closed position for a very long time. So over here, like if the circuit is closed, then the circuit will look something like this. 8 volt, this is 12 ohm, this is 9 ohm, and this is 50 millifarad plus minus V. Right now we know that the current, like since over here the capacitor is there, so since the circuit is in this state for a very long time, so the current over here it will be zero because of this capacitor. This capacitor is going to charge through this voltage source, and at the end it is going to assume, it is going to get the polarity, get the voltage as 8 volt, and because of this 8 volt present over here, this voltage supply will not be able to supply any current through this part of the circuit. However, this 8 volt will keep on providing the current to this, right? But the voltage across the capacitor, it will be 8 volts. So we can say that VC, or V, simply V, it is 8 volt, right? Now when this switch it is open, now as this switch is open, so our state circuit is now like this. And now since this battery is not connected to the circuit, right, so this battery will not be able to provide any current, so it is not going to provide any current to this 12 ohm, so this current will not be there, and to the capacitor this current was already not there, right? So our circuit, it will this source will not be able to provide any current, so we can simply remove this. So when the switch is open, our circuit will look like this. And now over here you can see that this 8 volt that is there across the capacitor, right, due to the charge, accumulated charge within the capacitor. So with this 8 volt, that is with the energy that is stored in this capacitor, with that energy the capacitor will try to keep the current, right? But the flow of the current will be in this direction, right, will be in this direction, right? So over here, if we know that for this type, we know that if we have this type of circuit RC, right, and if this is V, right, so we know that for this type of the circuit VT, it is expressed as V naught. V naught is the voltage at t equals to 0, and e power minus t upon RC, right? So using this same thing, we will try to over here in our circuit we have two resistors, right? So we will try to bring our circuit to this form. Now if you look at this, our 12 and 9 ohm, they are in series, so we can combine. So this will be 12 plus 9, so it is 21 ohm, right? C is already there as 50 millifarad, right? And our V, this V, initial voltage, it is the initial voltage, because this is the voltage at t equals to 0. At t equal to 0 means it is the voltage when we just open the switch, because once we open the switch, this voltage is going to decay. Why it is going to decay? Because this voltage is there due to the stored energy within the capacitor. But since there is no battery, so capacitor is going to use this energy to keep the current going, but this energy will be dissipated through these resistors, right? Through these resistors, the energy of the capacitor will be dissipated, and hence the voltage across the capacitor will be reduced with time. So it means that at t equals to 0, V is 8. It means that our V naught, this V naught, it is 8 volt. So now Using this, we know resistor, we know capacitor, we know V naught. So our Vt, it will be 8 e power minus t upon Rc. Rc is our Rc, it is resistor is 21 and 50 millifarad means 50 into 10 power minus 3 farad, or simply 0.05 farad, right? 0.05 farad. So it is 0.05. So over here I get 8 e power minus t upon, it is 1.05 1.05 and it is volt. So this is our equation. The voltage across this capacitor will be reduced with time as per this expression, right? So this is the expression of the Vt, voltage across the capacitor at any time. And to verify this, like if you substitute the value, if you substitute t equals to 0 and determine V, then this expression, this term, it will become e power 0, so it will be 1. So we get V0 as 1, and that is like our V0, this. So this proves that it is true. Also, if you put t equals to infinity into this expression, then you will get V infinity, it will be 8 e power minus infinity, which is equals to 0, right? And this also validates our expression, because as the voltage is going to decay with time, and since there is no external voltage supply, so the voltage across the capacitor keeps on decreasing, and at the end it will become 0. So having this formula, now we will come back to the question. Let me put this Vt that we got over here, 8 e power minus t upon 1.05, right, volts. Now over here, the first question is that we need to determine the current time constant. Now we know that in general the expression is written as this. In the denominator it is this tau, it is a time constant. We know that for the RC circuit, time constant is given as RC. So simply we do not even need this, right? We simply, like, we have the values of this R, we have the value of C. So simply we can determine the time constant without having this expression. But over here, since we have already determined the expression, so directly in the denominator, over here in the denominator tau is there, in the denominator 1.05 is there. So the answer to the first part of the question can be determined either by using this formula, by substituting the values, like R is 21 into 0.05, so simply we will get 1.05 seconds, or comparing this equation with the standard one, with this one. So comparing this, we will find out that tau is equals to 1.05 seconds. So this is answer to the first part of the question, where we need to determine the circuit time constant. Now the second part of the question says that we need to determine the expression for I1t. I1t is this current, means we need to determine this current, or this is I1t, right? Now over here, since we know this voltage, and this is the voltage across the capacitor, this is the voltage across the capacitor, right? Now if this is the voltage, the current through the circuit, it will be expressed as, using the Ohm's law, the current is V upon R, right? So our V, the voltage, it is this, so it is 8 e power minus t upon 1.05 upon R. R is total, it is 21, like for our circuit it is 21, right? It is 21. So it means that our IT I1t. It is because the same current, like in this circuit, like same current is flowing through all the circuit elements, through both the resistors and through the capacitor also, right? So we get this. So it is 8 by 21 e power minus t upon 1.05 amperes. So this is the expression of the current I1t. So this is the second part of the question, where we need to obtain the expression of I1t which is valid for t greater than 0. Now the next part says that we need to determine the power dissipated by a 12 ohm resistor at t equals to 500 milliseconds. So we know that power, it is I square R. So it means first I need to determine the I square at t equals to 500 milliseconds. So at 500 millisecond, it means it is 0.5. It means it is 0.5 second. Now substituting this t in this I1t, so we will get I1t will be equals to 8 by 21 e power minus t is 0.5, so 0.5 upon 1.05 amperes. So solving this, if you solve this, you will get 0.2366 ampere, right? And now once you get this value, substituting this value over here, you will get P is equals to 0.2366 square into R. R is, now over here we need to determine the power dissipated at 12 ohm resistor. So it means that our R, it will be 12, right? And solving this, you will get something like 0.6719 watt. So this is the answer to the third part of the question, where we need to determine the power dissipated at 12 ohm resistance at t equals to 500 milliseconds. So with this, I end this video. If you have any doubt, you can put it in a comment box. Do subscribe my channel and share this video with your friends and colleagues. Thank you.